Hey guys, I'm going to be going over the solutions for the AtCoder Beginner Contest 178. I didn't do the contest this morning because I had a very, very bad night of sleep and just didn't think I would be able to do anything. So I skipped it. However, I did the problems afterwards and now I can go over the solutions to all of them. So we're going to do that. Yeah, and that will be it. Let's do A. So A is simple. You are given a number, either 0 or 1. If it's 0, you print 1. If it's 1, you print 0. Now there are a million ways to do this. You can just read in the number and then do an if statement. Like if it's 0, print 1. If it's 1, print 0. You can also, for example, read it in as a Boolean and then print like the not of that, which is conveniently what the problem's called. Or you can do some like bitwise stuff and print that number XOR 1. Because if you see, that will give you exactly what you want. There are a lot of ways to do it. You just have to do any of them basically. On to B. And B is a problem. So you're given 2 intervals. This one interval is, let's say, the red one, and then you have a green interval. For example, -4, -2. And what you want to do is you're going to form a rectangle with side lengths x and y. So for example, like this. Actually, no. Would that work? Okay, no. Never mind. There's no reason to make it a rectangle. You're just looking for the maximum possible value of x times y, where x has to be within the interval. So in this case, x is between 3 and 5, and y has to be within its own interval. So y is between -4 and 2. Now, to maximize it, you want to have like the biggest number. So let's say there are a few cases you can do here. So let's say let's call this interval A and interval B. Actually, no, we'll just call them x and y. So let's say both x and y can be positive. Then one possible answer is just the maximum on x and the maximum on y. If x and y can be negative, or if x and y can also both be negative, then the answer could be the minimum on x and the minimum on y. Oh, wait. It should be minimum times minimum. And otherwise, so if both of these are possible, you need to check both of them and then see which one's better. However, sometimes it's possible that like you can't do either of these. For example, in this case, y is forced to be negative and x is forced to be positive. So what happens here is you want to make the negative number as close to 0 as possible. So you'll want to take the maximum on this, or the minimum on the positive one and the maximum on the negative one. Because if you decrease it anymore, then like it would be worse. So it's either min times max or maximum times minimum. Jesus, can't even write. Okay, and it's fairly simple to show that like you always want to be on one of the extremes, because let's say we had 4, then either it would be better to make our number higher or it would be better to make our number lower depending on which of these cases we have. And so if it's in the middle, then we can always make it either higher or lower, so it'd be better to do that. So this is all we have to check. If x and y can both be positive, it's max times max. If x and y can both be negative, it's minimum times minimum, and otherwise it's forced to be this. However, we don't actually have to do the casework. We can just check out all of these and then see which one is the maximum. Because even if this isn't the optimal answer and x and y both can't be positive, we don't really care because it's still a possible answer, so it's not like checking it is going to hurt us in any way. So the answer is just the maximum over all 4 of these. Yeah, it becomes that elegant. Now we'll do C. And C has an element of combinatorics, which I don't like. So there are some very simple solutions. There are some like simple solutions that use combinatorics. For example, one I heard was 10 to the n minus 2 times 9 to the n plus 8 to the n. I'm pretty sure it's that. And that's what I heard from other people. I'm not exactly sure why that works. Although it kind of makes sense. There are 10 to the n possible sequences in total. So it's kind of inclusion-exclusion. So there are 10 to the n sequences in total. Right. Then there are at most, there are 9 to the n sequences with no 0. There are also 9 to the n sequences with no 9. And then there are 8 to the n sequences with neither. So in sort of an inclusion-exclusion thing, we add the thing that has everything, then we subtract out the ones that have exactly, or at least, at most one of them, and then we add back the ones that have exactly none of them. And it's kind of like inclusion-exclusion. So if you know that, this solution works. However, I am not good at math myself, so I came up with something different that's kind of more algorithmic. So let's fix the number of 9s we have. Let's call it count of 9s. Then wait, I'm gonna make it n9 because I'm gonna use C later. So we fix the number of 9s, and the number of 9s is at most n, so we'll just iterate through it. Then what? So let's say we have some sequence. So we have x, 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 and we have 3 places for 9. So we can put these 9s basically anywhere. So this is basically 5 choose 3. We have 5 places to put the 9s, and 3 9s we have to put down. Or more specifically, 5 choose n9. Or rather, n choose the number of 9s. And then the rest of these can be anything. However, we have to make sure that we have at least one 0. Let's say the number of zeros has to be at least 1. So the combinatoric style here is to essentially we count the total number of sequences, which is anything that isn't a 9. So we can make all of these elements 0 to 8. We have 9 possibilities. So we have 9 to the n capital N minus n9 minus the count of 9s. But then we have to subtract out the sequences that are invalid. And the only sequences that are invalid are the ones that don't have zeros. So if a sequence doesn't have 0, every element is not 0. So any element can be between 1 and 8. So there are 8 possibilities. So there are 8 to the m minus n9 sequences that we have to subtract out. And this is the number of valid ways to fill in the rest of the numbers once we find the location for the 9s. So there are this many ways to find a location for the 9s, and there are this many ways to fill in the rest of the numbers. So the answer for this value of n9 is just like the product of these, because they're both independent of each other. So this formula will work generically. I'm going to move this down. Come on. This is stupid. Yep, okay. So this is the formula basically. When you fix the number of 9s, you have n choose n9, and then you have multiply that by 9 to the n minus n9 minus 8 to the n minus n9. And then you just do this over all n9s and you add them up. So for example, n9 equals 1 because you have to have at least one 9 and then up to n. So in terms of implementation and actually computing these things, there are many ways to do this. For n choose k, you can compute it like n factorial divided by m minus k factorial times k factorial. If you don't know how to do modular division, I will link my blog on modular arithmetic so you can learn from that. And it also has ways to compute all of the factorials in O of n. So you can do all of this in O of n, and then you can get a factorial in O of 1. So the n choose k will be simple to do. And in terms of this is modular exponentiation. So it'll take O of log mod. So the final solution is like O of n times log of the mod, which is 10 to the 9th plus 7. While this is technically constant, it's important enough to be included, so I will include it. And yeah. So one way to do it is to use inclusion-exclusion. Another is to fix the number of 9s. And just do some simpler, in my opinion, simpler math to figure that out. Okay, now we're on to D, and D is very standard. You're looking for the number of sequences where the terms are all integers greater than or equal to 3. So there's also a combinatorics way to do this, I suppose. I'm not going to go into that. You can try and derive it on your own, because I don't really understand it myself. But there is an even simpler way. We can do dynamic programming. So let dp of I be the number of ways to get a sequence of arbitrary length. Because we don't care about order, for example, 3, 4 is the same as 4, 3. We can just let dpi equals number of ways, or number of sequences with some I. And then how do you get to dpi? You have to add some number to some other sequence. So for example, let's think about dp of 5. Or we'll do like 7. I don't know. That's the sample. So 7 can come from just 7 itself, or you can stick a 3 at the beginning and then add dp4, because now you have a 3 and then you want to know the number of ways to get a sequence of some 4, so you can stick that 3 on to the end or the beginning, either way. And then you have a 4, and then you have to also add dp3, or you could have a 5 and then you'll add dp2, which is 0 because you can't get 2 at all, and 6 dp1. And you can also stick on a 7 and then dp0. So the base case here would just be that dp of 0 is equal to 1, because you have exactly one way to get a sequence with no elements that has some 0. So that is your starting point. And then the remaining formula is dpi is equal to the sum from 0 to I minus 3 of dpj. And that's basically the exact thing that's happening here. We can put down a 7 and come from 0. We can put down a 6 and come from 1, 5 and come from 2, 4 and come from 3, or 3 and come from 4. We can't put down a 0, a 1, or a 2 because those are not at least 3. So we have to start, or we have to end at I minus 3 because like we can't put down a number that's less than 3. An equivalent way of thinking about it is dpi is the number of ways to put down a number k greater than or equal to 3 and then take the dp value of the remainder. So for example, k equals 3 up to I of dp I minus k. And that's essentially you put down a number k at the beginning or the end, and then the remaining answer is just the number of ways to get the sum I minus k, which is dp I minus k. Or the number of sequences with sum I minus k that you can put this at the beginning of. So that's another way to think about it. Both are equivalent, so you can do either, whichever is easier to implement. Actually, they're the same, but yeah, basically a dynamic program. That is D. Okay. Now we're on to E. With E, you're given a bunch of points on a 2D plane. I'm going to use the sample. So we're given 1, 1, 2, 4, and 3, 2. So I'll label these 1, 1, 2, 4, and 3, 2. Okay, let's assume these points are sorted by x value. So we can just sort the points by x value. You can do this in many ways. For example, store a pair of x and y, and then you can just sort those specifically, because it'll first sort by x and then by y, but you don't really care how it's sorted by y. You just want to sort them by x. So let's say we're looking at some point here. There are two cases. Either the point is to the left or to the right. And because we're only looking for the maximum distance, not any sort of like pairwise stuff, we can sort of just assume that the point is to the left. Because if there's some point to the right, then when we look at this point later on, we'll end up considering this distance when we're centered at this point. So it's okay to only consider this point as the right point and then assume all other points are to the left. So that part's fine. And now what we need to do is figure out how to efficiently get the farthest distance from any point to the left of this. Okay, now this is a kind of well-known, I'm not sure. I think it is well-known, but the way to do this is essentially, let's just play with the formula a bit. So the formula for Manhattan distance is, let's assume we're at point I, and we're comparing the distance to some other point j. Then the distance is the absolute value, actually this is even given in the, this is even given in their statement. So it's xi minus xj plus yi minus yj, absolute value of both. But already we've made an assumption that makes this simpler. We know that xi is greater than or equal to xj because xi is on the, or because point I is going to be on the right. Or it's going to be at the same y coordinate, in which case it doesn't, or same x coordinate, in which case it doesn't matter. So we know xi is greater than or equal to xj, which means we can actually just cut out this absolute value, because no matter what, this quantity will never be negative. Okay, so now this is our formula. We have xi minus xj plus the absolute value of yi minus yj. So we can again break this down into two cases. Let's solve for, let's draw an imaginary line like here, and we'll solve for all points assuming they're above this, and then we'll solve for all points assuming they're below this. The reason this works is because, let's say we have a point here, and we assume this point is above I. Then, we'll consider this point later on when we check for all points below I, and with the way the formula works, it's essentially going to take, longer, or the distance is going to be less, because we assume it's above, but it's actually below, so we end up having a negative y distance, which means it doesn't hurt to consider this point as if it's below, because it's going to be less than our actual answer for it. So because we're taking the maximum of everything, we can get away with just considering all points that are below it. So now let's mess with the formula. First, we assume yi is greater than, we assume yi is above, so we're considering this half. Then the formula is just xi minus xj plus yi minus yj. Notice that two of these coordinates are fixed, so we can kind of split it up into the x part and the y part. So we have xi plus yi minus xj plus yj. So this part is fixed. All we care about is finding the minimum of this quantity, or rather, the maximum of this quantity. The maximum of negative xj plus yj. This is what I do in my code, right? I just want to make sure. Yeah, there's some stuff going on here. Okay, so we want to find the maximum of this quantity, or the minimum of this quantity. Either works. I think that's what I did, take the minimum, but again, either works. And so the way you can do this is just by keeping a prefix maximum over this quantity for all points that are before I. And if you can do that, then you can just ask for the prefix maximum at every point, and then you can immediately find the answer for all points that are below I. So we can do the same thing for yi is less than or equal to, doesn't matter. It can be equal to or not, yj. Now, this quantity is always negative, so to get rid of the absolute value, we have to negativize the whole thing. So we end up with still xi minus xj plus the negative of this quantity, which is just yj minus yi. So we can break this into an x part, or an I part and a j part again, and this will be xi minus yi plus yj minus xj. And in the exact same fashion, we just take a prefix maxima over this quantity, and then because this part's fixed, the answer for this point is just the maximum over this two. And then the answer for overall is the maximum over all points. And yeah, so you can do prefix maximums as follows. Let maximum of I be the maximum of all points up to I. Then the maximum of I is equal to AI. Whatever A is, for example, A would be the purple, the stuff in the purple boxes here. It would be the maximum of AI and all elements that came before it. Since we already know maximum of I minus 1, this is the new element, so we just consider it when taking the full maximum. but we already know the maximum of all of the other elements. So that's a simple way to do prefix maximums. And yeah, that basically does it. You just basically manipulate the equation to get rid of the absolute value. That's the key part here. Okay. Now we do F. F is a interesting problem. And I'll admit, the most elegant solution I found I did not come up with myself, but it's the one I'm going to describe because it's really, really nice. The problem is very simple. You're given two sequences of length n. Both of them are sorted. Sorted in non-decreasing order, so ascending, essentially. And let me find a sample that actually works. Let's try 1, 1, 1, 2, 3, and 1. I'll just mirror it. No, it doesn't work. Whoops. Wait, we'll do 1, 2, 2, 2, 3, and 1, 1, 2, 2, 3. That works. Okay. And we want to reorder the elements of B such that no element of B is equal to an element of A. So for example, these elements are all equal, and we don't want that. So we have to find any valid reordering or say it doesn't exist. That's the problem. So a very cool solution is as follows. Let's just write out A on top, and then we'll reverse B. So now B will be sorted in descending order. Now, the key part here is that there are only a few places where A is equal to B. Specifically, it's going to form an interval. Here's kind of proof why. So let's say, first of all, either there are no points where they're the same, in which case, like, that's easy, or there is at least one point where they're the same. Now let's look at one of these points where they're the same. So for example, here and here. So we know that there's a 2 here, and we know that there's a 2 here. We also know that everything on this side of the array is less than or equal to 2, and everything on this side of the array is greater than or equal to 2. And similarly, everything on this side of the array is less than or equal to 2 because it's descending, and everything on this side is greater than or equal to 2. So the only things that these points the only thing that this side can have that are the same are 2's. This is the only intersection between negative infinity 2 and 2 to infinity. Like, that's the only common point is 2. And the same thing is, and of course this doesn't have to be 2, this can be any arbitrary value. And the same thing goes here. The only intersection point is 2. So if there's an intersection at 2 where A and B are the same at a point where they're both 2, then the only other points where they can be the same are 2. Are where they're both 2. Because anywhere else it's impossible. It's not possible for there to be an element less than 2 on both arrays at the same time on one side, or greater than 2 on a side. And because the arrays are sorted, all equal elements are going to form contiguous intervals. For example, all the 2's are going to be together. So what that means is that there's going to be some interval where everything's equal, and then everything to the left and right is not equal, and then everything else is also not equal. So there's only some interval where they're all equal. So let's consider this now. So we'll use this array again. So I'm going to drop the color scheme. 1, 2, 2, 2, 3, and 3, 2, 2, 1, 1. So now the interval is here. And by a similar fashion, like, we can show that every element that's equal to 2, but not in the interval of equality, that is here, is going to be to the right in A and to the left in B. Because if there was a 2 here, and it matched with a 2 in A, like, it would either match on one of these sides or one of these sides. Like, if there was a 2 here, and there was a 2 to match with on A, actually, that might not be true. Never mind. No, actually, no. That's wrong, because it could be, like, 3, and then this can still be 2. Okay, never mind. Ignore that, but still all the 2's are going to be attached. Like, they're going to be next to each other. And there isn't going to be any matching between these. So there's some interval in A where there's some interval in B where each element is opposite a 2, but it's not a 2 itself. And there's some interval in A, possibly non-existent, where each element is opposite a 2, but not a 2 itself. We don't really care about the interval in A. What we do care about is the interval in B. So we have to move these 2's out. We have to move them to some positions that don't correspond to 2's in A. And of course, we can't swap them with other 2's in B. So that leaves only a certain number of positions where that leaves only a certain number of positions where we can move these 2's out. Specifically in this array, it's anything before here and anything after here. We have 2 2's to move out, so this is enough. We can swap these 2 elements and swap these 2 elements, and then the final array B will be 2, 3, 1, 1, 2. And that, as you can see, has no intersections. So the way to implement this like prefix and suffix swapping is kind of, you can do like 2 pointers, where you have a pointer to the left, and then you move it along each time you do a swap until you can't do swaps anymore. And you also have a pointer to the right, where you move it along to the left until you can't do swaps anymore. Or you can just have a single pointer and have it sweep through the array and make a swap every time you can. It doesn't really matter how you do it, actually. What does matter is that you don't do it in O of n squared. So yeah, don't do that. But anyway, however you implement it, you can basically just make the swaps happen. Now, the hard part is seeing why this actually works. Why is it correct? So let's assume you have, let's do some numbers. So let's say the number, I'm going to keep using 2's. Actually, let's say the magic number is x, the number where there are equal elements of A and B and their value is x. So then we'll let AX be the number of unmatched values of x in A. For example, this would be 1 because this 2 doesn't have anything to pair with. And BX be the number of unmatched x's in B. In this case, this would be 0 because there are no extra 2's. And then we'll let MX be the number of matched values of x. Or rather, the number of positions where there are x's in both places. So for example, here, there mx is equal to 2 because there are 2 places where both things are 2. So the total number of 2's we have, we'll let this be the count of x, is equal to the number of unmatched 2's on top, plus the number of unmatched 2's on the bottom, plus 2 times the number of places where both things are 2. Now we have to count the number of positions we have that aren't part of this. So any position where there's any 2 at all, we can't swap. All the positions where AX is the thing and BX is a thing and MX is a thing is independent. Because we can't, by their definitions, it can't be true that there's 1, 2 in A and 1, 2 in B unmatched at the same position. So AX, BX, and MX are independent. And in all of these locations, we can't make a swap. So we have, in total, MX swaps we have to make. And the number of free positions we have is n minus ax minus bx minus mx. So we want mx to be greater than or equal to n minus ax minus bx. And let's also minus mx. So now we have we can move this around a bit to say ax plus bx plus 2 times mx is greater than or equal to n. Which also means this is just the number of x's we have, because this is cx. So we can make this as cx is greater than or equal to n. So this is the condition for it being possible. Wait, that seems wrong. Sorry, this should be, mx should be less than or equal to this. My bad. Because otherwise we have too many swaps to make and we don't have enough places for them. Yeah. So the final condition is that the number of x's must be less than or equal to n. And if you think about it, like, this just has to be true no matter what. Because say we have 6 2's in total. Like, where do we put them? This is kind of pigeonhole principle right here, where if we have 6 2's to put in 5 places, at least one of them is going to have overlaps. So we can use the pigeonhole principle basically to prove that if cx is greater than n, it's always impossible. So this strategy only fails when it's already impossible by some other like logic. So and otherwise, like, it's always going to succeed because we can just move the 2's out to somewhere else. And because we're making new positions with 2's, like, there's no way we make any more matches that we have to get rid of. So once we move the 2, if we can move all the 2's out, we're just going to be done. And the condition for moving the 2's out is just that the number of 2's is less than or equal to n. So that is kind of an informal, formal proof of why this is correct. Either it finds a solution or it's impossible anyway. Yeah, either it finds a solution or there is no solution. It's that simple. So that's how you do F. And yeah, this solution is very, very cool because the implementation is like incredibly short. So yeah, I did not come up with this myself, but it is beautiful. Yeah, okay, that is all the solutions. I think so. Upcoming next is the edu round on coforces. I will not be able to do that because it's right in the middle of school, but I can make a solutions video and get into that. 19th. That works. There's some other contests that are doable, right? Like these ARCs, for example. Okay. Yeah, anyway. So upcoming with the edu round, I'll make a solutions video, much like this one for that contest. And that will be it. Yeah, I hope you enjoyed. Hope you understood everything. If you don't, leave questions as always. I will link my blog to modular arithmetic for C, so you can use that in the description. And that is all. Goodbye.